Hello, and welcome to another episode of MAIN-iac Science Lab. I'm Mr. Andy, Youth Services Librarian for the St. Johns County Public Library System here in St. Augustine, Florida. And today we're going to talk about science. In this episode, we're going to talk about a simple machine and one that you can make a scale model of using very, very simple household materials. All you need to build a replica of this machine is a pencil and a ruler. Maybe some tape too could come in handy. And then you need some sort of weight. And in this case, I'm going to use a stack of pennies. So if you have some pennies lying around, you can use those. Nickels work too, dimes, or whatever. You can use Legos, it doesn't matter. Whatever you want to use to get creative with your machine. So the first step you'll need to build your machine is to take your pencil and some tape and attach some circle tape loops to your pencil. The reason being, when you lay your pencil on a surface, it's going to want to roll around. Sometimes very effectively, but this time we don't want it to roll. So we're going to put two little loops of tape, one at each end of the pencil, to hold it in place and keep it from rolling across our surface. There's my second loop. I just fold it on itself, stick one at each end of the pencil. So then you can place your pencil on your surface, press it down, and now it doesn't roll anymore. Maybe a tiny, tiny little bit, but that's okay. So the next part to building your machine is taking your ruler. Find the 6-inch mark, because you have a 12-inch ruler, theoretically. Find your 6-inch mark, which is the midpoint of your ruler, and place that midpoint on the pencil. Voila! You have just built a machine. No, really, you did. It's an actual machine. It is. True. Does it look like something that you might recognize? Maybe something you've seen on a playground? Perhaps? What if I did this with my fingers? That's right. You've built a small replica of a seesaw, also known as a teeter-totter. Did you know that it's actually a machine? How can that be? Well, you've been to a playground, you've seen these, you've gotten on one before, you know how they work. We're going to use our little friend Jabba the Hutt as our test subject here. And he's going to say, I'm going to the playground. Doobie-doobie-doobie-doobie-doo. Oh, look, a seesaw. I'd like to play on it. Do-do-do-do-do-do-do-do. So he walks up, he gets on the seesaw, and what happens? We've all done it, because somebody always gets on first. This is what happens. It falls to the ground. Sits on the ground, Jabba sits there, gets bored very quickly, and realizes this toy is no fun at all when you're playing by yourself. Why? Because you need someone on the other end to apply downward force to lift him up into the air. And then he can apply downward force and back and forth, and you guys can alternate the force load on your seesaw, making it go up and down, seesaw, teeter-totter, whichever way you like to talk about it. And that's how it works. So, okay, let's pretend Jabba's here, and he's sitting on the seesaw, and he doesn't have a friend with him that day. He's there with his dad. So he invites his dad to come and get on the seesaw, and Dad sits on the seesaw. What happens? Or something similar. Have you ever tried that with your dad, where he gets on the seesaw on one side, and you're on the other side, and suddenly, boink, you're up in the air, and no matter how hard you try, you can't get him to budge. Well, what if I told you that if you could manipulate that seesaw, you could get him to budge? And that's where we're going to use our pennies to show how this works. So let's take Jabba, we'll put him over there somewhere out of the way, and we're going to use pennies to replicate two children or two people on a seesaw. And let's say each penny is 10 pounds. So on one side, we're going to have 1, 2, 3, 4 pennies, which equals to a 40-pound child. We'll put that one on this end. And then on the other end, we're going to put 1, 2, 3, 4, 5, 6, 7, and 8. With 10 pounds per penny, that makes an 80-pound child, your large friend, or larger than you friend. And put them on this side. And we know what's going to happen, right? The heavier friend goes down, the lighter friend goes up in the air. But you don't want to be up in the air. You want to go down, or maybe balance. Well, in order to do that, you have to apply additional down force, right? Well, you don't want to just suddenly put on 40 pounds just so you can play on the seesaw. But if you moved the seesaw, did you know that if you moved it, you can lift that heavier weight? It's true. Right now, we're at the 6-inch mark, which is halfway across the lever. Let's move it to the 5.5-inch mark and see what happens. No change. Let's move it to the 5-inch mark and see what happens. Still no change. Let's move it to the 4.5-inch mark. What? Suddenly the 40-pound kid hits the ground and the 80-pound kid goes up in the air. How does that happen? It's science. And our machine has just, well, it worked. It did what it was supposed to do. So what is this magical machine which can lift 80 pounds using 40 pounds? It's called a fulcrum and lever. So the fulcrum is a point at which a lever rests or is positioned on that the lever then balances on or is pivoting on. And in this case, our fulcrum is the pencil. The lever is the ruler. Now, a lever is a rigid bar that rests on a fulcrum, the ruler resting on the pencil, that will be used to move a fixed load, the 80-pound child, by exerting downward pressure force, the 40-pound child, on the other end of the lever. Now, the amount of downward pressure force required is reduced greatly by extending the lever end of, well, extending the pressure force end of the lever. The object is on this side. If you shorten the distance between the object and the fulcrum, extend the difference between the fulcrum and the pressure force being applied, the amount of pressure force required is greatly, greatly reduced. So by putting this, let's say this is at the 4.5-inch mark, at 4.5 inches from the weight, and then 7.5 inches from the fulcrum, 40 pounds will lift 80 pounds without even breaking a sweat. So how could this work in a real-life situation? In a full-size fulcrum and lever? Well, let's say you have a large object you need to move. Say you have a large rock in your backyard. It's too heavy for you to just pick it up, too heavy for you to just push it. Your body cannot physically move this rock. Can you build a machine that will help you move it? Well, this is an example of that exact machine, the lever and fulcrum. If you were to get a long piece of wood, like a long rigid board, maybe a 2x4 or a 4x4 or a 2x6, a thick, heavy piece of wood with a really long distance, and then you were to push that wood under the rock, wedge it under the rock, place a fulcrum under the board that you're using, and by getting that fulcrum closer and closer to the rock, the amount of downward force you would have to apply to that board to pull down will be drastically reduced in order for you to be capable of moving that rock you could not move all by yourself. That is how a lever and fulcrum work. It increases your ability to move heavy objects by reducing the amount of force required to do such. So, theoretically, given that, at the midpoint, 40 pounds does nothing to 80 pounds. But if you bring it back to about 4.5 inches, suddenly 40 pounds will lift 80 pounds easily. A scientific mind would think, well, at some point, 40 pounds and 80 pounds would be balanced, right? Well, it is. It's possible. Somewhere between that 6-inch mark and the 4.5-inch mark is the sweet spot to where the forces are balanced, and then the lever will float and each end will remain in the air. Now, it's a very, very minute, it's very difficult to get to that exact point, but it can be done if you have the patience and fortitude and your pencil doesn't move very well. But the best I can do right now is get it to where the weights shift very slowly as opposed to very quickly and violently. See, that moved a lot slower than that. That's very quick. Oh, we're so close. I could do this all day, but I don't want to waste your time. There we go. That's pretty good. Oh, so close. But you know that if you find that exact spot on the fulcrum of the lever attaching to the fulcrum, you can make it to where 40 pounds and 80 pounds balance in the air perfectly. And that's something you can try on your own. So that is a simple machine, the lever and fulcrum, how it works. This is in scale, but if you did the same thing outdoors with much larger materials, you can move much larger weights than this little stack of pennies using your new tool. And it's been used over the ages for mankind to move things over and over again. Every time you need to move something big, you get a special tool, and then you can do it. A lever and fulcrum is that tool. So, I hope you learned something. I hope you had fun with your experiment. I hope you play with it some more and see if you can find that sweet spot to balance the two disparaging weights on your lever and fulcrum. But for MAIN-iac Science Lab, I am Mr. Andy, and representing the Youth Services team here for St. Johns County Public Library System in St. Augustine, Florida. Until next time, keep experimenting, keep learning, and have fun. Bye.